So let us continue our discussion on the time period of a compound pendulum. In the previous lecture, we derived this formula which says T is twice pi under root I upon mgl, where the L stands for the distance between the point of suspension and the center of gravity Though this formula appears to be perfect, there is an issue when we try to apply this formula in practice. In order to find out T, we must know the moment of inertia I of this body of any random shape when it oscillates about an axis passing through point O. So it is pretty much difficult to find out this value of moment of inertia I. So we have to modify this formula so as to get a form suitable for experiments. For that purpose, we use the famous parallel axis theorem. According to this theorem, we assume that there is an imaginary axis passing through point G, which is the center of gravity, and let us call Ig as the moment of inertia of the same body about an axis passing through G. Now we have a relation between these two moments of inertia I and Ig. Since this distance is L and mass of the body is m, according to parallel axis theorem, we have this relation which says I equals Ig plus ml squared. So the moment of inertia about an axis passing through point O will be the summation of moment of inertia about an axis passing through point G, that is the center of gravity, and just the product of mass of the body and the square of the distance between these two axes, which is L in this case. So we can substitute this equation in this formula to get T equal to twice pi under root Ig plus ml squared upon mgl. Now we know another definition which is called as radius of gyration. To understand this concept, suppose that there is a body of mass m which oscillates about an axis passing through a point O, and we note that its moment of inertia is I. Now we choose a random axis and we choose another point mass which is having the same mass as that of the previous body, and we have to place this point mass at such a distance k that the moment of inertia, say Ig, of this mass will be same as the value I. Such a distance k, which offers the same moment of inertia as that of the previous body, will be called as radius of gyration. And since this is a point particle, the moment of inertia, according to the definition which we have already studied, will be just m into k squared. Now this second equation is to be substituted here to get t equal to twice by under root mk squared plus ml squared upon mgl, which gives us t equal to twice by under root k squared by L plus L by G. Now this modified formula is of much practical use than this previously used theoretical formula. So we will keep this in mind that though sometimes some formulae appear theoretically well, when we try to do some experiments, we have to modify accordingly. Okay, now we can check, or we can introduce another term which is called as equivalent length of a simple pendulum. Now in this equation star, if we put capital L equal to k squared by L plus L, with this substitution, this equation star would look like twice pi under root L by G, which is the time period for a simple pendulum of length L. So what does that mean? We can compare two pendulum masses, one which is a compound pendulum oscillating about point O, which is at a distance L from the center of gravity, and there is a simple pendulum having string length capital L chosen such that this capital L is just k squared by L plus L. So we are claiming that time periods of both these bodies will be same. So this capital L is called as equivalent length of simple pendulum. From this equation, another thing is clear. Since t is a function of L, which is straightforward from this equation, so as L changes, t is going to change. That is, t is a function of L. So if we choose different axes passing through different points O, say axis 1, axis 2, axis 3, axis 4, and then we can measure the time periods accordingly, center of gravity is going to be fixed. So what changes is this distance L1, L2, L3 and L4. So as this distance goes on changing, the time periods will be different. So t is a function of L, that is the distance between point O and point G. So we can try to find out a possible maximum value of t and a possible minimum value of t, that is the length corresponding to t max and t minimum. So for which lengths L, this body offers maximum time period and minimum time period. So for that, again we will use another principle from calculus. When we say that f is a function of x, which is having some random shape, and we are supposed to find the extrema, what we do is we differentiate that function with respect to x and equate it to 0. So this condition gives us the value of x for which f is extreme. F is extreme. Extreme in the sense either minimum or maximum. So accordingly, we will take this formula of t, which is twice pi under root k squared by L plus L by G, and let dt by dl be set equal to 0. So for that we must be able to differentiate this equation, which we have labeled as equation star. So dt by dl equals twice pi by root g are just constants, and we know that d by dx of root u is 1 by 2 root u into du by dx. So we will use this formula here to get an expression for the derivative. Fine. So this gives us 1 upon, now this is what our u is, right? So 1 upon 2 root k squared by L plus L into d by dl of the term inside the root, which is u here, and in this case this is just k squared by L plus L. Okay, we can continue this on the same lines, which gives us 2 pi by root g, 1 upon 2 root, all these things are same. Okay, now this k square is a constant because the derivative is with respect to L, and derivative of 1 by L is minus 1 by L squared, plus derivative of L is 1. So this is nothing but, let us cancel this 2, pi upon root g root k square by L plus L into, or let us write it as the numerator 1 minus k squared by L squared. Fine. So this expression is nothing but dt by dl, and now we are going to equate these to 0. Now just by looking at this equation, we can see that there are two conditions when this entire thing becomes 0. The first condition, when this entire thing becomes 0, is simply when k squared by L squared is going to be equal to 1, so that this subtraction becomes 0. In this case, k is simply equal to L. Fine. So we have with us one condition for extrema. Now there is second condition, condition 2, which is slightly tricky to understand, because now we have to focus on this part which is in the denominator. Now if suppose say L tends to 0, since L tends to 0, in this term root k squared by L plus L, this L goes to 0. So since L goes to 0, 1 by L tends to infinity. So this entire term tends to infinity. and this entire term is sitting in the denominator. So it becomes 1 upon infinity, which again tends to 0. So this entire term now tends to 0. So the second condition is when L tends to 0. Since L tends to 0, it means that point O and point G coincide. Point O and point G coincide. So what does that mean? The pendulum does not oscillate at all. How is that possible? The pendulum remains in equilibrium forever. So in such a case, how much will be the time period t? We know that as per the definition of time period, it is the time required to complete one oscillation or one revolution or one cycle. So if the pendulum is going to be in the same state forever, when we start time t equal to 0, we say that pendulum is never going away and coming back to the same position. That means the time required for the pendulum to come back to its original position will be infinite. So this condition L tending to 0 is the condition of maximum time period, which is infinity. Okay, so we have established that this condition is the condition for maximum. So obviously the second condition is going to be the condition for minimum. Fine. So we have both the conditions with us. So t is twice pi under root k squared by L plus L upon G. In this case, T max happens when k equals L. Now if we substitute k equals L in this equation, L squared by L give us an L plus L will be 2a. So this is 2 pi root of 2L by G, or just 2 pi root of 2k by G, because L and k are same. And T minimum is simply tending to infinity, and it occurs when L equals 0. So these are the conditions for maximum and minimum time periods. We will extend this discussion further to understand another important property of a physical pendulum, which is sometimes called as reversibility or interchangeability. What does that mean? That a compound pendulum is a reversible pendulum. So it can oscillate with the same time period at two different points. So just for the discussion purpose, again I will write the formula here because we will need it again and again. K squared by L plus L by G. Consider the same pendulum. Let us call this as point O, this as point G. This will be the distance L. Now we have to consider another point along the line joining O and G, but on the other side of O, and call this as point O dash. This is just an imaginary point, and we can call this distance to be L dash. And in principle, we can revert this pendulum and make it oscillate about an axis passing through O dash. In that case, this will be L dash, this will be G, and this point O will be now point O, which will be below G. So this is just reverted. Since pendulum is suspended from point O, this is called as point of suspension. And this point O dash is free to oscillate. It is called as point of oscillation. Point of oscillation. So these are just the nomenclature. Now we will express the time periods about O and O dash. So first, time period about O will be twice pi under root k squared by L plus L upon G. Now remember, we have chosen, or we have to choose L dash such that L dash is equal to k squared by L, or k squared will be L into L dash. So this is our choice of L dash or of point O dash. So if we substitute this for k square in the equation above, we get t equal to twice pi under root LL dash upon L plus L by G, which is just twice pi under root L dash plus L upon G. So just remember this expression, twice pi under root L dash plus L upon G. Okay. Now we will try to find out the time period about point O dash. So we will call it as T dash. So T dash will be just twice pi k squared by L dash plus L dash by G. So this is equivalent to the previous formula. Only the change is that we are replacing T by T dash, L by L dash, because this new time period is about point O dash. Now again we will substitute the same equation, k squared is LL dash, to get T dash equal to 2 pi LL dash by L dash plus L dash by G, which gives us twice pi under root L plus L dash by G. Now we can compare these two expressions and we see that these two are same. Twice pi under root L dash plus L by G. So this means that T dash is going to be equal to T. That is, for a compound pendulum of any random shape about point G, we can find two such points O and O dash such that even if the pendulum oscillates about O or O dash, in both the situations the time period will be going to be the same. So it doesn't matter whether we oscillate the pendulum about point O or point O dash, because it offers the same time period of oscillation, and that is the reason why this pendulum is called as a reversible pendulum. Thank you.